And here they're using not x equals cosine t, but y equals sine t, right? I went through that x equals cosine t and y equals sine t so that you understand in the circle context where it's coming from, right? Now I want you to be able to think like this. T is input, right? And typical letter for output that represent output is y, right, in mathematics. Typical letter for input is x. So eventually they switch to x. So you will see y equals sine x. I hope at this point you don't get confused with x and y in the coordinates of a circle definition. But this is simply just dummy variable for whatever that input for the sine and whatever the output for the cosine. I mean the output for y. But I'd like to still stick to this t for a while so that we talk about the motion a little bit. And when we talk about just the algebra or analytic geometry of this thing, they tend to use the y equals sine x. But let's get comfortable with y equals cosine t, this thing. This is alright? Y is just a dummy variable for vertical axis. T is to represent horizontal axis. Feel comfortable with, y representing cosine. Okay? Yeah. So that's what this one is. Y equals sine t, y equals cosine t. T is the horizontal axis representing the time. Y is vertical axis, maybe the displacement of the mass attached to a spring system. Okay? So there is this graph here, y equals sine t and y equals cosine t. This is the extended version. We know, although we sketched only this bit, we understood that it goes to the right and left forever in the xy plane, right? And here's a ty plane, and as well. All right, so if you look at here, the motion starts here and go up and down. Motion start in cosine graph in the top and bottom and below. And if you just look at it here, removing the x-axis and y-axis, then it seems like the same wave, right? So it is not really different in terms of and how often you go up and down. So here's the new term we're introducing here, period, right? Period is time, how long it takes to do something. Okay? How long does it take to Earth revolve around the sun? 365 some days, right? That's the period. To repeat one motion a cycle. After that, you repeat kind of the same motion cycle. So that's one cycle is one rotation, and period is how long it takes. And they're saying period here is 2 pi, and they're indicating this length is a period. Usually period represent a number and not the interval. Okay? You see the difference between a number and interval? Interval is not a number, it's some portion of a number line, things like that. All right, so what is 2 pi in general? Roughly it's 6.2. I'm doing this so that you accept this 2 pi is magnitude of time, not magnitude of angle. If I do that, I think students have a better understanding psychologically. Hey, 6.2 second makes sense. 2 pi second is kind of weird. Things like that. All right. So that's that. There's 6.2 seconds. So what does that mean? After 6.2 seconds, what happens? During that 6.2 second period, what happened to the mass attached to spring? It completes one cycle of motion. Sine graph, it starts at the equilibrium position, go up and down and come back up. That's one cycle of motion. How long does it take in this graph? 6.2 seconds, 2 pi seconds later, it come back to the equilibrium position and repeat the same thing. And here it says this is going to give you the period. It's exact same 6.2 seconds. This time cosine motion is that it starts at the top and goes to the bottom and coming back up. So that's the motion like this. And after that it repeats exactly the same cycle of motion. How long does it take? 6.2 seconds. That's the idea of a period. All right? You can see that if I put something heavier or something like that, and you could move slower, and you know of that. So that's going to change the period. All right. There's also a notion of something called a frequency. This algebraic relationship between frequency and a period is very simple. So once you understand the relationship between, conceptually understand relationship between period and frequency, then I want to leave that and rely on this algebraic relation, which is easy to memorize and handle. All right, so think about guitar string. All right, how long does it take to complete one cycle? If I pluck the string, maybe 0.1 inch, and I release it, and it's gonna go below the equilibrium position and coming back up. How long does it take? You can imagine this like a millionth second or something, right? Small. So that's an inconvenient number. So they changed it. All right, I give you 1 second and see how much of a 1 cycle motion happens. That's a better number than 0.000, things like that. So there's a note A in the guitar string. If you plug that one, you measure 1 second and see how many times the guitar strings go up and down repeated. Turns out it was just roughly about 440 times per second. That creates musical note of A. Right? So they write it. This is some important number in the science. They put units there. It's 440 hertz. If you have the tuner at home to tune stringed instrument, they have this thing built in. All right? How many times? 440. So what do you think it's how long it takes to repeat one cycle? How do you calculate that? You wait 1 second, it's repeating this. For example, that's a cosine motion is more natural for plucking guitar string, right? You pluck it up here and release it from the top position, go bottom, and that's more like a cosine motion. So it repeated 440 times in 1 second. So how long will it take to repeat one cycle? Let's 6.2. Let's experiment. Let's do it a little bit. What if it is 2 hertz? What does that mean? I waited 1 second, right? And then it repeated 2 times. 2 motions. So to repeat one motion, how many seconds is it required? Period. Somebody says 1/2 seconds. After 1/2 second, it repeated one motion, right? After another 1/2 second, it repeated another motion. So in 1 second, you got 2 cycles, correct? Does it make sense? Right. Let's do 3 hertz. What does that mean? 3 cycles, right? Per how many seconds? 1 second. For 1 cycle, how many seconds is it required to make a 1 cycle? Period. Period is how long it takes to make a 1 cycle. 1/3 second. Does that make sense? So you got the pattern? You have 440 times repeating like this, and for one cycle, and what is the period here? 1/440. Now you punch in the calculator, you got that number. So at that short period of time, the guitar string will go back and up to create that musical note of A. All right. If you hit it by 2, which is 880, that's 1 octave high. If you multiply by another 2, that's another octave high in the musical notes system. All right. So yes. Important part, but for our course, we learned this differential equation. The phenomenon of the frequency is completely separated from how much you pull it out. That is not easy to understand. So in the mathematical equation, this forces and its innate tension inside it's completely separated in mathematical equation. So we see that when you're doing this differential equation thing, but just qualitatively discussing this one is puzzling. And as far as I know, many engineering professors and physics professors, when they introduce this one and also use that, this is not easy to understand. It's a kind of magical thing is happening. Doesn't matter how hard you pull it out, time it goes back and forth, it's going to be the same. All right. That's the second. That first part was also already magical. Why is that? How hard you pull it out? Why is it hurts so the frequency is the same? That's weird mystery, right? And then there's a damping force. Something is stopping this down, right? Air friction is very minimal because of the momentum is really high. So it is the string tension that is damping it down. Now there's an additional damping forces in there. And why is the damping force is not changing the frequency? That's the second, even harder to understand. Right? Yeah. So that's kind of strange. But that's called this is called a simple harmonic motion. Just keep changing. It does not, the amplitude, the oscillation amount does not change. It's a simple harmonic motion. In reality, it dies out. It's called the damped harmonic motion. Right? We're only going to do the simple harmonic motion in here, but you're going to learn in detail the damped harmonic motion in differential equations. And that is it's really fun to learn, and how this damping, how the forces interact in mathematical form. Anyway, what we just learned here is a relationship between the period and the frequency, right? So the period is P number, and how do you calculate frequency? 1 over P hertz, right? And P second, is that right? If I give you P second, 1 over P hertz, that's the frequency. And vice versa. If you have a frequency and to calculate the period is reciprocal. That's how things are related. Make sense? All right. Like I did, and like I introduced the graph of sine and cosine, we're going to go through some long discussion to understand what this problem is asking and how I help you to understand this one. Once you understand, you just focus on the shortcut, right? So we're not going to repeat this. This is something you did in an earlier algebra course. It's about sketching the graph of a function, and here they're using the function form. I'm going to switch to t notation. So here, example of part A, I'm going to use it like this: y equals a 2 plus cosine t. Okay, y equals 2 plus cosine t. So it is cosine t plus 2, and this is going to be again a motion, and we want to sketch this one. And second one is a negative cosine t. All right, if it is just y equals cosine t, you put the reference point and those two top lines, right? Y equals 1, y equals negative 1, and sketch the cosine, and that's what you have to do. Now, is a 2, in terms of transformation of a function, do you know what this 2 plus is doing? Let me list the transformation. There's a vertical shift, there's a horizontal shift, there's a reflection across the y-axis, reflection across the t-axis, and there is a horizontal shrinking and stretching. There's a vertical shrinking and stretching. These are the transformation, easy to describe and easy to understand. And there are, of course, other types of transformation. It's not as simple as those. So do you see this is one of those? Vertical shift, thank you. Everything, the graph you looked at a second, y equals cosine t, is going to shift it up by how many units? Positive 2 or negative 2? Positive 2 units, right? So here's how we're going to sketch. You're not going to go through the procedure of shifting all that. We're going to just do something that this, realize it. Hey, there's a vertical shift by plus 2 units. That means upward by 2 units, right? Okay, so we're going to focus on some of the things that it's affected. So what are the reference points? When I was sketching the reference points, were those mainly t coordinates or y coordinates? T coordinates, right? What were those coordinates? Reference points of cosine t? 0, pi over 2, pi, 3 pi over 2, 2 pi, right? those t coordinate, when I shift it vertically, those t coordinate changes or does not change? Don't change. They don't change. So I'm not going to pay attention to that. What about that amplitude lines? As you move it up and down, you can see that coordinate changes, right? So I'm going to write down those amplitude line. Y equals 1, y equals negative 1. Is that right? What are those? Why am I writing those? Those are the dotted line, amplitude line, right? We're going to shift it by how many units? 2 units. So what's going to happen to that? 3. And this one here, positive 1. Right? Negative 1, you add 2, it becomes a positive 1. Right? So you're going to put this 2 dotted line at 3 and 1, and you're going to go through a cosine graph there. That's how you're going to sketch this one. And this is in a chapter 3. If you're not remembering this transformation business clearly, then you have to look up that chapter 3. Functions, in that you will find, transformations of functions. So here's a 1, here's a 2, and here's a 3. All right? So you look at y equals 3, then you're going to put this nice dotted line there. And y equals 1, you're going to put this nice dotted line there, right? And cosine is going to oscillate in between this strip, within this strip, right? All right. Where do you see the equilibrium position? It helps to put that. Before it was there as a part of coordinate axis. This time it's not. So we're going to put this right in the middle. It's easy to see that as y equals 2, right? But just in case this is some ugly number, a, and y equals b there. If you want to find the what in the middle, do you know how to do that quickly? It's the average of in between. So what would that be? The formula, the midpoint formula, a plus b divided by 2. If the number's ugly, you can't quite see where exactly the middle part is. You add those two, top and bottom, as coordinate exactly, and divide it by 2, and that's the exact coordinate in the middle. That principle goes to x coordinates as well. Some of us have a trouble to what is the midpoint of, pi here and 2 pi there. Remember why I'm bringing this up? Those are one of the reference points in our cosine t and sine t, right? What's in the middle, right? That was a question. You add these two, that's 3 pi, right? Divided by 2. So that's 3 pi over 2. That's a quick algebraic way of dealing with how to find the middle one. Make sense? All right. So here we do the same thing. Here's a 3 and 1. You add this 2, 4 divided by 2. That's why it's a 2. Different way to see it, if it's not clear. This is a cosine graph, right? Only transformation involved is the vertical shift. So where is this graph is going to start? Top of the amplitude line or the bottom of the amplitude line or equilibrium position? Cosine graph? At the top of the amplitude line, right? It starts right here. Okay? So this is 1, so it's 2, 3, 4, 5, 6. It's roughly where this is 2 pi. This is pi. This is pi over 2. And this is 3 pi over 2. Now I just use a rough estimate of 6 to locate 2 pi, and then you just keep bisecting these intervals to get this pi and pi over 2 and 3 pi over 2. Make sense? Yeah. So you get this, you started right here, and then it's going to pass through equilibrium position at pi over 2, remember that part? What happened to pi? Bottom amplitude line. 3 pi over 2, where does the cosine go? Equilibrium position again. At the 2 pi, it hits the very top. That was a cosine graph the reference points of the cosine graph. Cosine graph hooks like this and make a little bit of straight line looking, and then hook it like there. Straight line looking, go down like that. So that's the graph of cosine, shifted vertically by 2. Make sense? Yes. That is a cosine graph. If it is a cosine graph, you start at the top of the amplitude. If it is a sine graph, it starts at an equilibrium position. Okay? All right. So that's the vertical shift business. Let's look at the second example. Any question, by the way? Does shifting business make sense? All right. All right. Yes, Kirsten. The second example there is this y equals, what is it? Negative cosine t. Transformation. Who would like to go for the transformation of this one? Multiplying negative to whatever that stuff is in the right hand side. Vertical shift, horizontal shift, reflection, x-axis, t-axis, and y-axis, horizontal shrinking, vertical shrinking. Which one is it? Reflection. Now, is this a reflection across y-axis, so points are going across like this, or across the t-axis? If you do y-axis, which coordinate changes? X coordinate changes, right? If you cross the t-axis like this, t coordinate doesn't change, right? But y coordinate changes. Originally it was y equals cosine t, but y coordinate changes to negative. So therefore, it must be reflection across the horizontal axis, right? So this is reflection about t-axis, right? But it doesn't mean the t coordinate changes. It's actually the other coordinate changes. That way is a bit confusing, but it's reflection, right? About t-axis. Make sense? Here is a point in here. If you cross a t down there, t stays and y coordinate changes. Think about that. All right. So, when you reflect across the t-axis, do you think the t coordinate changes? Well, here's a little side notes in here. I have 2, 3. T is 2, y is 3. Reflector across the t-axis is down there, right? T won't change. Only the y coordinate changes. Is that right? Therefore, we don't have to worry about the reference coordinate of t there, right? That's going to be exactly the same. 0, pi over 2, and so on. So I'm not going to write down anything about the reference point. How about amplitude line? Y equals t and y equals negative t. They're reflected. Y equals t go down to negative 1, right? Y equals negative 1 goes up. So you're going to write it like this. Y equals 1, as you reflect it, that amplitude line becomes what? Negative 1. And y equals negative 1 becomes a positive 1. So it's in a different order, but it's the same line. After I sketched it and show the result, you won't distinguish the original one, and you don't know which one is sketched first, right? Unless I use a different color. So amplitude stays the same, but something changes, right? So here is our graph. T here, that's 1, 2, 3, 4, 5, 6 is roughly 2 pi's here, pi over 2, there and there. Is that right? All right. Then here's our amplitude line. It's going to be real squares in. This is 1 and negative 1. Okay. The cosine starts at the top amplitude line, right? If you reflect it across the t, that's what we're about to sketch. Where do you think it starts? At the bottom. All right? Reflection across the t-axis, that makes it start at the bottom. All right? So, like a guitar string, you're not pulling up. You're actually pressing it down and release it from there. Okay? It's like my thumb movement. I actually play a guitar. When you use a plucking with the other fingers, you're going to pluck it upward and release it. But if I use a thumb, I press it down and release it from there, so it is kind of starting at the bottom, right? So it starts at the bottom and reflected image. I hope this one is natural to you. Going in there like this, and the bottom like that. Is this all right? It's reflected across the t-axis. All right. Again, which chapter? Chapter 3, transformation. If that Doesn't ring a bell. All right. That's y equals negative cosine t. All right. Do you remember how many transformation I listed? Was even number. All right, we're going for that. Let's look at this. Is another important example. All right. So I'm going to change to YT thing again. Am I recording? Yes. Y equals negative 3 cosine t. All right. Is order of operation important? In general? Yes, right? And there are some order of transformation you go through, and you end up at different result if you do it in the wrong order. Okay? So make sure you understand that. How about this one? This is not a one operation in here. We started like this. Let me analyze it like this. Y equals cosine t. This is what we understand. And let's go through something familiar. Something we just did. Right? It's a negative cosine t. So I'm going to write the negative cosine t. So if I change from cosine to negative cosine t, what transformation are we going through? Reflection, right? Do you remember what type of reflection you're going through? About which axis? Was it t-axis? Think about a little bit of the reflection to understand this thing. What is the one more thing we have to do to arrive here? This is multiplying 3 there, right? Multiplying 3 is negative 3 cosine t. That's what this is about. Correct? So what is that transformation we're applying here? Shift is adding. If you add 3 plus 3, then it's a vertical shift. But if you multiply 3, it's not shifting. Horizontal stretch and vertical stretch. In this case, it's a vertical stretch. All right? So this is a vertical stretch. By how many, what kind of factor? We call it a factor. By factor 3. Not negative 3. Negative 3 is taken care of in a previous step. Alright? Alright, let's look at here. Graph was there. Reflecting across t-axis. Does that changes our t reference points? Doesn't. Right? How about stretching vertically? I realize that this is not really natural to many people, so I'm going to explain a little bit. I have, let's say, like this. This is part of the parabola. You agree? And part of the parabola. I'm about to stretch a factor of, for example, 3 like this. By stretch, let me write it clearly, correctly. Vertical. It's not vertical. It's vertical stretch by, let me use a simple by factor 2. Factor 2. What does it do to this graph? We have to understand that, right? So not like shifting, but it's different. If I have, let's say that was 1, 0. That was a 3, 0. Let's say that was a 2, 1. And this parabola passes through this point. We're about to do this vertical stretch by factor of 2. And what's going to happen to these 3 points? Let me explain. That is a perfect answer. That is exactly right. So vertical shift is adding that number to the each coordinates, right? That was vertical shift. And the vertical stretch is multiplying. Algebraically simple. Just multiply that. Shifting was algebraically simple. You add, also easy to understand geometrically what it's doing to that whole thing is shifted up, or just what I just did. I shift this graph just by 200 pixels down. I just did that, right? That's the vertical shift. So what I'm going to do next here is this, and what this one is doing is a 2.1, and we're going to do, nothing happens to the x-coordinate. The vertical is only the y-coordinate. What do we do the y-coordinate? We multiply that factor 2 right there. Okay? So if this is a 1 unit, what happened? stretched by 2 times. So it's going to be over there. This is going to be 2 times 2. So just for that point is shifted by 1, but the shift amount is different. So that's not the way to understand. What's going to happen to that point, you think? 3 comma 0? You multiply 2 to that second factor, remains exactly the same. Because 0 times 2 is 2. So this guy don't go anywhere. Let me go ahead and sketch it. What about this point? Coordinate is not important. What we're going to do is that you keep the y coordinate and just multiply the y coordinate to is roughly here. Is that right? Does that make sense? The y coordinate is 2 times. And here let me use this point, different point. Y coordinate is 2 times. I just stretch the y coordinate, and each point the amount it goes up is different, but multiplicative factor is the same. So I'm going to just smoothly connect this one like this. And the Paint, Microsoft Paint, and all the other art software, if you grab something, you can horizontally stretch and vertically stretch. They have this pixel and XY plane. They exactly use this simple operation. You multiply the y coordinate pixels and x coordinate pixels by this one. That's how you create this thing. If you do horizontal stretch and vertical stretch by the same factor, that will be exactly, keeping the ratio and blowing up in exactly the same thing. That's the vertical stretch. All right? So, going back to our important information in sketching these graphs, amplitude lines and what is happening to those reference points. And then we can sketch it, right? Now, we have reflection. So let's see that at this stage, y equals 1, y equals negative 1. What are those? Anybody remember the name of this thing? Amplitude lines, right? Go through the first, what is the first transformation? What is it? Reflection. So we got that y equals, what was that? Negative 1, and y equals 1. Switch the order, but it's the same collection of lines. Next thing is a new. Stretch by factor of 3. It's this line is there. If you stretch it vertically away from x-axis and y-axis, right, like that, right, then you multiply 2 there, right? So it's negative. In this case, the factor of 3. How about that? So you multiply 3. So negative 1 times 3, y equals 1 times 3. So it's a 3 and negative 3. Now amplitude is wider, and that reference point is still the t reference point is still the same. Okay? So I would like to make this one exercise. I want you to go ahead and sketch this amplitude line just like I did, and do your best to keep the same scale, because that matters and reflects your understanding. You draw this two amplitude line, this new amplitude line here, and sketch that t reference point that's exactly the same, right? And try to do this motion between this amplitude line. They're the same. So that's your exercise. So I recommend the first thing to do is sketching the amplitude line. Right, this picture reasonable? Right. So let's think about an motion. This is a 1-inch pull-up versus 3-inch pull-up, right? Versus. And they create the same frequency in our perception, right? So they go through exactly the same time period. And that's strange in actually what happens. All right? So this corresponds to, the frequency corresponds to the pitch of a sound, right? Do you know what this one corresponds to, this amplitude? How loud the sound is. Okay? So you can keep the same frequency and making the sound a lot louder. That means the air molecule is moving a lot more distance. Magically, their period and frequency is exactly the same. So that's interesting. Louder, exactly, yeah. Think about it, guitar string you pull up further away from the equilibrium position, you expect a louder sound. And that's why it's moving up and down a lot more like that. Okay? All right. Things been happening like vertically. Would you agree? Shifted vertically, reflected vertically about t-axis, stretched vertically, right? So we didn't touch those t reference points, right? This time we're going to do something different. So here is horizontal part. So here's part A is y equals 4 times cosine 3t. If it is just a 4 times cosine t, we feel comfortable with that, right? It's amplitude line stretched by factor 4, and you go through the same reference point. So this one is a vertical stretch factor. What is it? 4. Next one is strange. Horizontal stretch factor, this 3. By looking at the 3's multiplied in front of t, it becomes horizontal stretch factor. Horizontal stretch factor. So I'm going to put the stretch in quote. And what is that factor? Answer is not 3. Neither negative 3. 1/3 is the correct answer, right? In this multiplicative business, reverse of a multiplicative business is reciprocal, right? Addition business, reverse of addition business is subtraction. Now think about this side note here to business about horizontal transformation. Y equals t squared. Do you know what that is? Parabola, right? It's a parabola. Looks like this. Next one is t is changed to t minus 2 squared. T minus 2. This is a horizontal shift. Although your number you see here is negative 2, this is actually horizontal shift by how many units? Positive 2 units, not negative 2. Although you see negative 2 here, is actually positive 2 units. So if you sketch it, here's 1, 2, and then sketch it like this. You can verify it. If it is a 2, if you plug it in there, it becomes 0, right? So it's x t-intercept. Makes perfect sense. If you actually shift it to negative 2, sketch it here, if you plug in negative 2, you can see it's not 0. So that would be wrong. And this would be correct graph. In horizontal shift and horizontal stretch, the business is a little opposite than vertical shift and vertical stretch. That's something just to remember. If you want to understand why, here's one more tip. Because this equation is solved for y, not solved for t. Is that right? Y is on the left-hand side. Everything about t is on the right-hand side. So the situation is not fair for t. Right? It's not symmetric. That's what they say. Because of that, the business is done slightly different. Let me make it a little bit symmetric in here to confuse you further. Y divided by 4 is equal to cosine of 3t, right? This is not completely solved for y. Now, instead of y, you see y divided by 4, right? 1/4 is multiplied to y. So what is the vertical stretch factor? Not 1/4, but the reciprocal of 1/4, 4. So that principle goes exactly the same to this one. Instead of 3t, I see 3t. What is this horizontal stretch factor? Not 3, but the reciprocal of what is in front of it. That principle, if it is written like this, is consistent for y and t. However, if you solve this thing for y, then it began different. Why this is so confusing? Because we prefer solved form of y as a function. Now you can forget all these things. Just have to remember, if you see things in front of t, that's a horizontal stretch factor, and the factor is actually the reciprocal. Okay? That's all you have to remember. If you want to understand a little bit more, listen to my rendition again, or go to the chapter 3 and understand a little bit better. Why isn't the stretch in a coat? If you multiply that factor 1/3, what happened to the y coordinate? It actually shrinks, right? The stretch is not a good word. But you can, I hope that makes sense. Stretch factor 1/3, you understand it's actually shrinking. Is that right? So let me stick to this word stretch. If this factor is less than 1, then it's actually shrinking. All right, let's see some example of shrinking. And here, all right, here's our parabola again. 1, 0. What was the top one? 2, 1. This one was a 3, 0, right? What's going to happen to these points is that if I multiply by factor a 1/3, that's what we're talking about here, right? And this one is added or multiplied. It's a stretch factor that we're going to multiply to which coordinate? X coordinate. Horizontally, it has to be x coordinate. So, where do you think this one goes? 1, 0. 1, 0, you multiply 1/3 to that x coordinate. So 1/3, 0? Is that right? Therefore, it's somewhere right here. Agree? How about this guy, 2, 1? Where does that go? 1/3 multiplied to 2, 0, 2/3. So here's 2/3 is somewhere about here, right? That's where it goes. That's a 2/3, 1. Y coordinate never changes. How about this guy here? 3, 0. Right. Which is better known as 1, 0. So that guy shrink right there. Right? So we're going to connect these 3 dots in a kind of similar fashion. So we're going to have something like this. That's the shrinking business. Toward to where? Vertical axis. Horizontal shrinking. Now what's going to happen to our t reference point? They're going to shrink, right? So let's try if this is intuitive. So first thing we're going to do is that y equals cosine t. That's where we're going to start, right? And then let's do some familiar thing. 4 times cosine t. Feel comfortable with that? Vertical stretch by factor of 4, right? So it's going to amplitude line is going to be stretched away 4 and -4 like that, correct? Next business is changing t to 3t, right? Then this is horizontal stretched by what factor? 1/3, right? So we're going to do it like this. All right. What happened to amplitude line? Remember what happened to amplitude line? Multiply by 4. Vertical stretch, right? So I'm going to do it 4 here using this space as wisely as possible. 1, 2, 3, 4. Is that right? That's good. Now, at this stage, if you're in the second transformation, nothing happens to our t reference point. 0, pi over 2, and those stuff, right? Now we're doing, next business is called horizontal stretch. It's actually shrinking, right? The horizontal box size, what was that? It's starting from 0, and where does it end up at? 2 pi, right? So there's this box. Here's a 4. Roughly, here's a 4. There's roughly 6. So this is where roughly it's 2 pi. The cosine is going to go through within this box. Does that make sense? But what's going to happen to this 2 pi? Horizontally shrinking. So we're going to multiply the factor to this pi over 2, right? So what is that? 2 pi over 3, right? So I'm going to divide into 3 pieces. That's going to be 2 pi over 3. Makes perfect sense, right? 2 pi divided into 3 pieces, that's your 2 pi times 1/3. And I want you to think, where does this 1/3 come from? Anybody remember where the 1/3 come from? That coefficient in front of t turned to reciprocal because this how the stretch factor horizontally work, and multiply to our coordinate 2 pi. All right? Your cosine graph must be squeezed into this. Make sense? Yeah. Okay. So computing the coordinates, I'm going to do that later, but we have, if everything is happening within here, right? So we have divided into pieces like this. That's going to be the half of 2 pi, that thing is shrinked in here. Then another pi like that. Is that right? Those were the 5 reference points, usually all squeezed into this 2 pi over 3. Make sense? All right, where's the cosine graph starts? Top or bottom in this case? Top. There's no negative in front of it. There's no reflection. It starts in here. You go through the first reference point. Cosine hits right here, right? That's the first reference point, remember? And the second reference point is down here. Third reference point, it hits there. And there. All right? And repeats again in the second box. Agree? Repeats again in the third box. Like that. So this is how many cycles have I sketched it here? 3 cycles, correct. Start in here, go up and down, and this is where it was in the third one coming up there. Given 2 pi seconds, we repeated 3 cycles. Yes?
So if the coordinate, if the third coordinate of the t value is...
This one here?
No, over there in that graph, it's 3 and 0. So it's got to be 1 and 0. Doesn't that mean it should end one cycle at pi?
No, if you think about it, this motion, it starts at the top. When you come back up, and this is exactly where that time period is. That's one cycle. Yeah, it goes down and up, and that ended at that 2 pi over 3 seconds later. That is the period, right? That's an important thing I want to address. One cycle happened at 2 pi over 3. Is this roughly 3 point some seconds, right? So in this case, after 3 point seconds, you repeated one cycle. All right, so we'll do more of this period and frequency and amplitude that determines pure sound, pure wave.
So we can look at the
Formulas and decide it quickly, yes. Yeah.